This video is brought to you by mywayteaching.com.
In this part, let us learn electric field due to system of charges. Okay. Consider a system of charges Q1, Q2 up to Qn with position vectors R1, R2 up to Rn. Okay. Relative to some origin O. Like the electric field at a point in space due to a single charge. Electric field at a point in space due to system of charges, isn't it? If you place a single charge in the space, the electric field due to that. If you place system of charges in space, the electric field due to all those charges is considered. So that electric field at a point in space due to the system of charges is defined to be the force which is experienced by a unit test charge placed at that point without disturbing the original positions of these Q1 to Qn charges. For this, we can use both Coulomb's law as well as superposition principle in order to determine that electric field at a particular point P, which is denoted by the position vector R. Okay. You can see this figure. This is electric field at a point due to a system of charges. You can see Q1, Q2, Q3 are all considered at system of charges, and we are finding electric field at a particular point P, and it is considered here. And this electric field is nothing but the vector sum of the electric fields at the point due to individual charges. Electric field due to Q1, Q2, Q3, Q4. If you add all those things, then we'll get the electric field at point P. So the summation of this E1 plus E2 plus E3 plus E4 gives the electric field or the resultant electric field at the point P. Okay. Then the electric field E1 at R due to Q1. As you can see here, the electric field E1 is due to the charge Q1, isn't it? Whatever we have considered. So that is given by E1 is equal to Q1 by 4 pi epsilon naught R 1p square. And here also we can consider unit vector. So this is a unit vector in the direction from Q1 to P. That's why R1p. In a similar way, we can consider electric field E2 at the point P2 due to the charge Q2, isn't it? And here the position vector is R2p. So this is also a position vector from Q2 to P. So this R2p is the distance between Q2 and P. As you can see here, it is mentioned here. R1p is the distance between Q1 and P. Similar expressions hold good for E3 and E4, isn't it? Due to charges Q3 and Q4. Then by the principle of superposition, the electric field E at R due to system of charges is given by, as I told before, it is just the summation E1 of R plus E2 of R plus E3 of R. It goes on up to En of R. So we can also write it in terms of vector expressions. That is E of R is equal to 1 by 4 pi epsilon naught sigma Qi square Qi RIP square and a unit vector RIP. And here the E, it is a vector quantity and it varies from one point to the another point in space. And it is always determined from the position of the source charges. Okay. Now let us study what is the physical significance of this electric field. What is this electric field and why it is introduced is the question that's constantly coming in your mind, right? See, for any system of charges, the measurable quantity is the force on a charge which can be directly determined using Coulomb's law and the superposition principle. Then what is this electric field? See, for electrostatics, this concept of electric field is very convenient, but it is really not necessary. And this electric field is an elegant way of characterizing the electrical environment of a system of charges. Because whenever you consider electric field around a point in space, in system of charges, that electric field describes or it tells the force or unit positive test charge would experience if it is placed at that particular point. And this electric field is also characteristic of the system of charges and it is independent of the test charge that you place at a point to determine the field. And the meaning of this field in physics is generally it refers to a quantity that is defined at every point in space. Okay, and it may vary from point to point. Electric field is a vector field and since force is a vector quantity. If you want to really know the significance of this electric field, then we should go for the time-dependent electromagnetic phenomena. Which means if you consider the force between two distant charges like Q1 and Q2 in accelerated motion, now the greatest speed with which a signal or information can go from one point to the another is the speed of light. So the effect of any motion of Q1 on Q2 cannot arise instantaneously. Isn't it? There will be some delay between the effect and is even for cause. So here the notion of electric field is natural and it is very useful. So here the accelerated motion of charge Q1 produces electromagnetic waves which then propagate with the speed c and then they reach Q2 and they cause a force on Q2. So the notion of field elegantly accounts for the time delay, isn't it? That field should spread, it takes some time. So even though electric and magnetic fields can be detected only by their effects on charges, they are regarded as physical entities, not merely mathematical constructs. And these fields, electric fields, they can transport energy also. See, the concept of field was first introduced by Faraday and it is now among the central concepts in physics. Now let us see one more important example. An electron falls through a distance of 1.5 centimeter in a uniform electric field of magnitude 2 into 10 raised to 4 Newton per Coulomb The direction of the field is reversed, keeping its magnitude unchanged, and a proton falls through the same distance. Compute the time of fall in each case. Contrast the situation with that of free fall under gravity. You can consider figure A and figure B here. So in the first figure, the field is upward. So the negatively charged electron experience a downward force of magnitude E into E, where E is the magnitude of electric field. And in that case, the acceleration of electron will be force by mass of electron. So starting from rest, the time required by the electron to fall through a 2hme distance is given by through distance h, the time taken to fall through distance h is given by square root of 2h by AE, and here we know AE value that we have to substitute here. So we know the value of E, that is 2.0 into 10 raised to 4 Newton per Coulomb. H is 1.5 into 10 raised to minus 2 meter, and mass of electron is 1. Mass of electron is 9.11 into 10 raised to minus 31 kg, isn't it? And the value of the charge E is also, we know that 1.6 into 10 raised to minus 19 Coulomb. So after substituting all those values in this equation, we get the value of TE, which is equal to 2.9 into 10 raised to minus 9 seconds. Okay. This is the first part. In figure B, you can see the field is downward and the positively charged proton experiences a downward force of magnitude EE, and then in that case the acceleration is equal to EE by mass of proton, and we know the mass of proton is given by 1.67 into 10 raised to minus 27 kg. So in this case, the time of fall for the proton is given by, so for the second case, the time is, we can write it as Tp, that is given by square root of 2h by AP, and that AP we know. So here again we know the value of H, MP, isn't it? If you substitute all those values, we get the value of Tp as 1.37 into 10 raised to minus 7 seconds. So the heavier particle takes greater time to fall through the same distance. This is the basic contrast to the situation of free fall under gravity, where the time of fall is independent of mass of the body. And here we have ignored the acceleration due to gravity in calculating the time of fall. So in order to see that this is whatever calculated is justified, let us consider acceleration due to acceleration of the proton in the given electric field. Okay. That is given by, so acceleration due to proton is given by E by mp. So here we know E, we know E, and we know mp. Isn't it? If we solve this, we get the value which is equal to 1.9 into 10 raised to 12 meter per second. So this is enormous compared to 9.8 meter per second square, isn't it? The acceleration due to gravity. So we can see the acceleration of the electron is even greater because mass will be less compared to proton. So the effect of acceleration due to gravity can be ignored in this particular example. Okay.